Okay, so we're going to continue our discussion of classical statistical mechanics. And the next thing that we want to discuss is what's called the Maxwell-Boltzmann distribution of molecular speeds. Specifically, the question that we would like to ask is, what is the probability density for a molecule to have a specific speed, independent of direction of travel? So not a specific velocity, but a specific speed. And so far, we've been talking about the probability of our classical particle to have a specific momentum. Right? A momentum is a vector, it has both a direction and a magnitude, so it has three components, px, py, pz. And we started concentrating on just one-dimensional motion, so just in the x direction. Now let us go back and revisit what we said last time. What we said was that the probability for a classical particle, we have in mind a dilute gas of particles. The probability for a classical particle to have a specific, to have a momentum that falls in an infinitesimal range around a specific value. So the probability that the particle has momentum falling in the region between px, some value of momentum in the x direction, and px plus dpx, a short distance away from px, so an infinitesimal region, right? And we'd say that this probability, or this probability that the particle has momentum falling in this narrow range around a point px looked like this. It looked like the probability density, or probability per unit interval in momentum, which is a function of momentum itself, times the small increment in momentum. This quantity for a classical particle, actually I'm going to write this down here. Oh, actually, you know what? I'm sorry, I forgot about the fact that because of the glare, the very top line is very difficult to see, so I will try to write lower. So let me rewrite this. The probability that the particle has momentum falling in a small range dpx around some value px, depending on px, is equal to, let me rewrite this, e to the minus beta, where beta is the usual 1 over kBt, 1 over Boltzmann's constant times the thermodynamic temperature, px squared over 2m times dpx divided by 2 pi m kBt to the 1/2 power. This is for a classical particle moving in one dimension, moving in 1D. That's what we said last time. What about for 3D, a particle that's able to move in all three dimensions? In 3D, you would have the probability that you have momentum px and momentum py and momentum pz, or these are the components of the momentum vector. And this would look like e to the minus beta px squared over 2m plus py squared over 2m plus pz squared over 2m, now times dpx, dpy, dpz. And as I go through in more detail in the notes, right now we're just kind of summarizing and sketching out, and of course you look for the details in the notes and in the book. For each dimension of travel, one gets this factor to the 1/2 power. So in 1D, we have 2 pi m kBt to the 1/2 power. In 2D, you would have 2 pi m kBt to the 1/2 power squared. So just 2 pi m kBt. In 3D, you have 2 pi m kBt to the 3/2 power, because there were three integrals over three different momentum coordinates in the partition function. 2 pi m kBt to the 3/2 power. This is the probability that the particle, actually I should have this, sorry, on the left I should have, to be consistent with above, the probability density, right? Pz times dpx, dpy, dpz. So in words, the probability that a classical particle that is able to move in all three dimensions has momentum in the x direction in a small range dpx around some specific value. So the probability that the particle has momentum equal to some value within a small increment around that value, and the same thing for the y momentum and the z momentum, is this formula. Now for us, generally speaking, it's sometimes easier or more intuitive to think about velocities and not momenta. And so what if we wanted, instead of the probability to have specific momenta, the probability that our particle has a specific velocity or specific velocity components? Well, we know that the momentum, let's say in the x direction, is m times the x component of the velocity vector. Or put another way, the momentum vector is m times the velocity vector. And therefore, everywhere you see a px, for example, you can replace that by mvx. And dpx, oops, again, I should not be writing this very high up, apologize. So what I said above was that px is mvx. So this vector equation implies the equality, this relationship among the components of these two vectors. And so what this implies is that dpx, the infinitesimal increment in x, is d of mvx. M is a constant, so it comes right outside, and so this is equal to m dvx. And the same thing for y, and the same thing for z. And so where I see a dpx, I will replace it with this. Where I see a px squared, I would replace it with m times m squared v squared. Right, px squared is m squared v squared. Divided by 2m, you get 1/2 mvx squared. Kinetic energy, exactly what we would expect, right? Just an alternative way of writing kinetic energy. And so in terms of velocities in 3D, for a classical particle, the probability that the particle has some velocity in a narrow range between vx and dv plus vx plus dvx, and so on for y, and so on for z, this probability, now as a function of velocity components, is e to the minus 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. Forgot a minus beta if I don't want to keep writing kt, times m dvx, m dvy, and m dvz. The whole thing still divided by 2 pi m kbt to the 3/2 power. And so that's the 3D version. And the one-dimensional version from here is that the probability to have a specific speed in the x direction looks like, let me write it down, m 2 pi kbt to the 1/2 power e to the minus m vx squared over 2 kbt, now written fully in terms of Boltzmann's constant as opposed to beta. All I've done here is I've grouped the m's, so from each, if this is just one dimension, I get a factor of m here, but I also have m's in there. And so this is m to the 1 power. This is m to the would be to the 1/2 power if it's just for one dimension, and so you end up with just m in the numerator with a 1/2 power. And then, of course, multiplied by dvx. And so this is the probability that the particle has a specific component of the speed in that direction. Once again, it's a Gaussian function, just like it was for momentum. And so with this in mind, you can calculate things like the average x component of the velocity, which would be integral over all possible values of the component of the x component of the velocity, which can go from minus infinity to infinity. Right? Velocity can be forward or backwards, and that will correspond to forward and backward or positive and negative directions of travel. So there could be all possible values in the negative direction, all possible values of the x component in the positive direction. And this would look like Vx, the probability density, times dvx. And so you would plug in this probability density, multiply by Vx, and calculate the answer. And the answer, as we discussed last time, should be 0. On average, the particle is moving equally likely to move with some velocity to the left and to the right, and so you average out to 0. And you can also prove this to yourself by noting that this is an even function of x, this is an odd function of x. When you multiply an even function of x by an odd function of x and you integrate over all space, you get 0. And we discuss this in more detail in the notes. Similarly, you can find the square of the x velocity with the same prescription as before. And so one could, for example, want to find the root mean square speed. V in the x direction, let's say RMS, root mean square, which would be the square of this to the 1/2 power. And so in here, you would be averaging the square and then taking its square root to find the root mean square speed. And so that's how you would work with this distribution. Now, it is usually the case that you don't necessarily care in most situations about motion in a specific direction. For us, we chose the x direction just to choose a specific direction. The exact same formulas would be obtained for the y direction and the z direction, because there's nothing special about the x and the y and the z directions, right? Space looks the same in all directions, and who I call z can be changed and called x in the next kind of, for somebody else. So it's an arbitrary choice of coordinate axis orientations. And so this kind of a formula is true for both the y direction and the z direction, and it looks identical. Another way to say this is that motion in the x direction is not affected by motion in the y direction, and vice versa, and the same thing for the z direction. They exist as independent motions in a sense. So it is often the case that you would be interested not in the probability for the velocity to have a specific component, not in the x component of the velocity or the y or the z components of the velocity, but the magnitude of the velocity vector or speed. Right? Velocity has a magnitude and an orientation. The magnitude of the velocity vector or the norm of the velocity vector is the speed. And so speed is a quantity that just measures the magnitude of motion without regard of in which direction the particle is traveling. And most of the time, that's the kind of thing that you would normally care about as a chemist. Why? Because the speed with which molecules are moving determines the speed with which they collide. And the speed with which they collide determines the amount of energy within a specific collision. And the amount of energy within a specific collision determines whether that's sufficient or not to overcome some activation barrier for a chemical reaction. And so, but that we don't necessarily care about a specific motion in the x and y direction. We just care about just with how much speed are the molecules colliding. And speed is what determines the total kinetic energy. And so how would we go about asking that question? What is the probability that our particle has a specific speed, not a specific velocity component? And so let us think about this. how to think about this. First, we note that, or let us note, that the velocity vector can be represented in a number of different coordinate systems. Of course, you would have been familiar with this from your calculus classes. Maybe you haven't thought about this for a while, but let me remind you that if this is velocity space, so where the variables are the components of the velocity vector, a given velocity vector will have components in the x direction, components in the y direction, components, or rather a component in the z direction. But you can also locate this point where this vector points, or where this vector terminates, by a different set of three numbers. And that different set could be the spherical polar coordinates. The spherical polar coordinates locate this point in space where the velocity vector terminates via the radial vector. The radial vector here is the magnitude of the velocity vector, or the norm. The polar angle theta and the azimuthal angle phi, or phi. And so we can depict the velocity vector, or write the velocity vector, in terms of its Cartesian coordinates components, or in terms of its magnitude, or the radial vector, the radius, the azimuthal angle, and the polar angle and the azimuthal angle. And there exists well-defined equations that transform from one coordinate system to the other. What do they look like? Let's write them down. The first transformation equation is the Pythagorean theorem in 3 dimensions. And the Pythagorean theorem in 3 dimensions says that the square of the velocity vector, which what we mean by that is the square of the norm. Right? This is the norm of the vector is the length of the vector. And so this is the square of the length, or the square of this radius, is equal to the sum of the components. The sum of the squares of the components. This is the 3D Pythagorean theorem. The other equation relates the z component to the polar angle as the magnitude of the vector times cosine theta. And the x component is the magnitude of the vector sine of the polar angle cosine of the azimuthal angle. And the y component is the radial vector times the sine of the polar angle times the sine of the azimuthal angle. Of course, this is all in your notes, but let's just write it down for completeness. And so we have a set of transformation equations that will allow us to go from the coordinates in the Cartesian coordinate system to the values of the coordinates for the same point in space for spherical polar coordinates. Now, let me just also mention that it's conventional, as I mentioned here or above, to kind of define, if you will, maybe I should write this. The speed, right, is defined as the magnitude of the velocity vector. So everywhere here, I can replace that by just the symbol v, or what I mean is the length of this vector, or the norm of the vector v. And so I can just kind of make this replacement for now, so that I don't have to keep writing the norm of the vector. And so doing this requires that you rewrite the probability density. Rewrite the probability density in terms of the spherical polar coordinates. Usually you write the polar angle first by convention. But it also requires that you rewrite the infinitesimal increments to the spherical polar coordinate values. And what one finds, again, this is just can be looked up in a calculus book, so we're not going to go through the gory details of this. But what one finds is that dvx times dvy times dvz is equal to v squared sine of theta dv d theta d phi. So these guys used to be in the probability distribution, in the probability formula, now get replaced by this. So this is what's called the volume, the infinitesimal volume element in XYZ space. This would be the infinitesimal volume element in spherical polar coordinate case. And so if we do all of this, if we combine all of this, what we find is precisely the probability that our particle has a certain speed, but also a specific orientation. So this, let me just write this down again. This dvx, dvy, dvz gets replaced by a quantity written in terms of spherical polar coordinates times the infinitesimal volume element, which is v squared sine theta d theta d phi. And now we plug this in. And what this requires is to look at the exponential factor, the Boltzmann factor that we had before. And everywhere we saw a Vx and a Vy and a Vz, replace that by these variables. But in the Boltzmann factor, what this looked like was e to the minus beta. Actually, let me rewrite this. E to the minus beta m over 2, if I factor out the 1/2 m, vx squared plus vy squared plus vz squared. But remember that this thing is just the square of the vector, the square of the vector length. And so what we have is a quantity that looks like the probability to have the velocity vector have this magnitude or this speed and oriented such that it has angles theta and phi with respect to the polar coordinate axis system times the infinitesimal volume element v squared sine theta d phi equals, that whole thing looks like, we're going to combine all the constants, all the terms, m divided by 2 pi kbt, whole thing to the 3/2 power, e to the minus beta 1/2 m v squared, where this is now the speed squared, not the components, but the speed, or the magnitude of the velocity vector, times the infinitesimal volume element, v squared sine theta d phi. So this isn't just the probability that the particle, our classical particle moving in 3 dimensions, has a specific speed. This is the probability that our particle has a specific speed and that the velocity vector is oriented with these angles with respect to the axes. But if we want just the probability that the particle has a specific speed independent of the orientation of the velocity vector, using the exact same logic and the same reasoning that we've applied kind of throughout the entire course so far, this would correspond to the question of or based on our original rules of probability. What is the probability that our particle is traveling with speed v with a velocity vector oriented in this direction, plus the probability that the particle is traveling with the same speed v but now velocity vector oriented in this direction, plus in this direction, plus in this direction, plus in this direction, plus in this direction, summed over all possible directions, mutually exclusive outcomes, consistent with the inquiry, which was probability that the particle is traveling with a specific speed independent of orientation. So summed over all possible values of orientation. Or in this case, because the orientation is a continuous variable, by orientation we mean the set of these two angles, theta and phi. You have to integrate over the angles as opposed to sum. And so the probability that the classical particle has speed v independent of orientation, I can put this in parentheses, independent of orientation of the velocity vector. Is equal to integral over d theta, integral over d phi, but not integral over v. Times probability density, as it depends on v, theta and phi, times v squared sine theta, and that's it. Sorry, d theta, d phi are already in there. What are the possible values of theta and phi? Theta goes from 0 to pi. So this goes from 0 to pi. The azimuthal angle goes around the circle. So this is from 0 to 2 pi. Notice that we are not integrating over v, because we want the probability that the speed is some value independent of anything else, and so we're summing or integrating over the values of the orientation variables, the angles, leaving the speed alone. And so when we are done integrating over theta and phi, what results, the end result of all of that, will no longer be a function of theta and phi, like this quantity is. We will have what's called integrated them out. And what will remain is a function of v only, because v was untouched and not integrated over. And so this can also be rewritten as the integral from 0 to pi of sine theta d theta, the integral from 0 to 2 pi of d phi, times the probability density, with v being viewed as a constant as far as the integration is concerned, times v squared. And so at this point, one would plug in the formula that we had before. Notice that this quantity depends only on v. And so the integral over theta and the integral over phi does not affect this quantity at all. even though we write it formally as a function of v, theta, and phi, we saw that this thing had the Boltzmann factor in it. And the Boltzmann factor depended only on v squared, the magnitude, not the orientation. And so in a sense, this is a bit superfluous. We just did it for consistency's sake. And so these integrals can be performed relatively easily, actually quite easily. And I do this on the homework, in the notes, and you can look up the answer. So we're just going to move on past that and write down the celebrated result called the Maxwell-Boltzmann distribution of molecular speeds, which answers the question, what is the probability that a molecule chosen at random will be moving with some specific speed, falling in a small increment around a specific point, independent of where the velocity vector points, so independent of direction of travel. But what's the probability of a specific speed? And the answer is, let's write it down. Maxwell-Boltzmann distribution of molecular speeds. Molecular is given by the following quantity. When we put it all together, 4 pi, which came from the angle integrations, m to the 2 pi, or divided by 2 pi kBt, whole thing to the 3/2 power, e to the minus mv squared over 2 kBt v squared dv. This is the probability that a particle that has mass m moving in 3D has speed in a small increment dv around some value v. That probability depends on v, and it depends on v like this. It also, of course, depends on the temperature. They're both of these factors. And so let's plot this probability distribution. First, let's notice something. The functional form of this probability distribution, as it depends on v, contains two terms. One is a Gaussian, or a rapidly decreasing function of v. The other one is v squared, which is a parabolic function with respect to v, which is an increasing function of v. When you multiply a decreasing function of v by an increasing function of v times some constants, the answer is a function that displays a peak. Not a sharp peak, but a peak. And so oops, again, I forget about the fact that there's glare. And so let me just erase this. We were to plot just the probability density as a function of v. You would have a plot that looks like this. Just need to extend my axis. So that the probability to have very low speeds at some temperature is small, relatively speaking. The probability to have very high speeds is also relatively small, and the probability is maximized somewhere here. So this would be for some temperature. What happens when the temperature increases? The probability at a higher temperature might look like this. The probability at a much higher temperature might look like this. Again, I need to extend my axis. So this would be T1, this would be T2, this would be T3, where T1 is smaller than T2 is smaller than T3. What does this mean? This means that as the temperature goes up, the probability to have higher values of speed becomes higher. And so the probability gets extended and pushed to higher values of v. Notice that the peak value is going down. Why would the peak value go down? The peak value would go down because the probability must be normalized. And if you're extending the probability to higher values of v, the overall magnitude has to come down so that the area stays the same, because the area has to be equal to 1, because the probability is normalized. Right? It must be the case that if you integrate this quantity over all possible values of v, what can they be? They can start from 0 and go all the way to infinity. Right? Speed can be negative. This quantity must be 1 if it's a probability distribution. This point is the point for which the probability is maximal. We might call this the maximal speed. I'm sorry, not maximal speed, the most probable speed. Most probable. The way you would find that most probable speed is working with the Maxwell-Boltzmann distribution that we wrote down a second ago and finding its maximum value, or its extremum value, because it doesn't change sign. And to do that, you would set the derivative of that function equal to 0 and locate that maximum point. And that would be this. The average speed, unlike the x component or the y component or the z direction on average, is no longer 0 because speed can be negative. The way you find this is you would perform an integral of v times the Maxwell-Boltzmann distribution from 0 to infinity, and you would get an answer. I will just simply quote the answer for you as we do on the homework. on the notes. And the answer is 8 kBt over pi m to the 1/2 power. And so the average molecular speed goes as the temperature to the 1/2 power. It's an increasing function of temperature, which makes sense. The higher the temperature, the faster on average are the molecules traveling. For a given temperature, though, as the molecule gets more massive, the average speed goes down. And so really heavy things at the same temperature are traveling on average slower than really light things at the same temperature. And you can also find the average square and therefore the root mean square speed, and we do that also, or we write down the answer for on the notes. What's interesting about it, what does this show? This helps in a sense, or our first indication that will allow us to think about rates of chemical reactions, perhaps surprisingly or unsurprisingly. Suppose one needs to get to this V. I'm going to call this V. Actually, let me erase this. We know that the speed is related to the kinetic energy with which the molecules are traveling, right? So kinetic energy of the molecule, or average kinetic energy of the molecule, is 1/2 m the square of the average speed. And so the speed itself can be related to the average, to the kinetic energy. If the molecule is traveling with speed v, it has kinetic energy 1/2 mv squared. And so suppose a molecule needs to have some speed vc, where this is some critical speed with which the molecule can overcome a reaction activation barrier. Suppose that you know that for a given chemical reaction, a molecule must be moving this fast for it to have just enough energy to overcome the activation barrier for the reaction. And of course, if it's moving faster, it will also be able to overcome the activation barrier. What this says is that as you raise the temperature, you raise the probability that a given molecule will be found moving with this speed or higher, right? Because it's this area that represents, or this relative area that represents the probability that a molecule has this speed or any other speed higher than that. So the probability that the molecular speed falls in the range between Vc and infinity. And so the Maxwell-Boltzmann distribution gives you a very obvious way to think about how a chemical reaction will change with temperature. And of course, we're thinking about a gas phase system, a dilute gas phase system, close to the ideal gas situation. But generally speaking, if we don't worry about the details, this tells us that one of the ways to think about why chemical reactions increase with temperature, or rates of chemical reactions increase with temperature, it's because you get more molecules moving with larger speeds. Why do I say more molecules? Because the probability density can be related to the fraction of molecules that have that specific speed. This shouldn't be unfamiliar to us. We've seen this kind of in examples of when we talked about fractions of molecules in specific quantum states, corresponding to probabilities to be found in that state. And so the probability density for a molecule to be found with a certain speed is synonymous with the fraction of molecules of a total moving with that speed. And so what that means is that you can say that in words, let's write this down. If there are a total of n molecules, the fraction of molecules, fraction, not probability, but the actual fraction of molecules moving in the increment dv around speed v, right? The fraction of molecules whose speeds all fall in the small range dv, right around some specific value of speed. This is going to be equal to the probability, and the probability is a product of the probability density times the increment dv times the total number of molecules. I'm sorry, I shouldn't say fraction. This is the fraction. But the number of molecules moving with this speed v. Let me rewrite this. Right. That's as it should be. What I meant to add was the number of molecules, not the fraction and not the probability, but the number of molecules moving with speeds between v and v plus dv is the fraction that have that speed times the total number of molecules. In fact, let me say n total. And so by increasing the temperature, you increase the number of molecules or the fraction of molecules in your collection composed of n total molecules who have a specific speed. And therefore you increase the chance that the molecules have enough energy to overcome the reaction barrier, and therefore you expect chemical reaction rates to increase with temperature, ones that have an activation barrier. Okay, that's the Maxwell-Boltzmann distribution. There's obviously a lot more that could be said about it, but we've said just the very core things. The notes give you more information, the book even more still. But this gives you the very basics of the Maxwell-Boltzmann distribution of molecular speeds and the kind of calculations that could be done using it. What we're going to do in the very next follow-up video is to use the Maxwell-Boltzmann distribution and the results that come out of it to estimate a very interesting quantity, and that is the frequency with which molecules collide. And we're going to do this in a very rough, coarse way.